When engineers design control systems for complex machinery, like a multi-axis robotic arm, they face an immediate mathematical problem. It is impossible to physically test how a linear time invariant, or LTI, system will react to the infinite variety of inputs it might encounter in the real world. Instead of attempting endless simulations, we rely on a standardized testing suite. We use canonical input signals to probe the system and map out both its immediate, transient response and its long-term steady-state behavior. This chart plots the unit impulse function, denoted as delta t. It delivers an instantaneous spike of infinite amplitude and zero duration at time zero. Physically, the impulse is a sudden burst of energy. Because it excites the system across all frequencies simultaneously, the resulting output provides the mathematical basis to define the system's unique transfer function. This next chart shows the unit step function, u of t, characterized by a sudden, permanent transition from 0 to 1. The step input models a hard switch-on event. It tests how a system handles a sudden command to change states, which is the most common operating condition for power electronics and hydraulic valves. Finally, this visual displays the unit ramp function, r of t, which increases linearly over time. The ramp evaluates tracking performance. It tells us how well the system can continuously follow a moving target without falling behind. These three test signals form a unified diagnostic suite tied together by calculus. Integrate an impulse and you get a step. Integrate the step and you produce a ramp. By analyzing how a system reacts to this sudden step, we can begin to derive the governing equations and root locations that dictate its performance. This allows us to build a model that predicts how that same system will respond to other operational demands. We start by defining a standard first-order system. Governed by a single dynamic mode, its transfer function contains one pole and relies entirely on the variable tau, known as the time constant. Here is a circuit diagram modeling a physical first-order system. A voltage source drives a current, I1, through a single resistor and a single inductor. In this specific circuit, the time constant tau is derived directly from the ratio of inductance to resistance. It is the mathematical measure of the circuit's thermal and magnetic inertia. This plot maps the exact circuit's current response to a unit step input. It rises to a steady 5 amperes. Notice the definitive first-order trait, an exponential rise without oscillation. After exactly one time constant, the system reaches 63% of its final value. This graph compares our original response against two variations of the same system. The red dashed line represents a smaller time constant of 0.1 seconds, while the black line shows a larger time constant of 2.5 seconds. This establishes a rigid engineering rule. A smaller tau indicates low inertia, resulting in a highly rapid system reaction. A larger tau means high inertia, producing a sluggish climb to the steady state. First-order dynamics are highly constrained. Driven by a single energy storage element, they only have the capacity to charge or discharge exponentially toward a target. This updated schematic shows what happens when we introduce a second energy storage element, in this case, a capacitor. The circuit now requires a second loop current to resolve. Because of that second component, the system is now second-order. Its transfer function's denominator expands into a quadratic equation, introducing two vital new parameters. The first is omega n, the natural frequency. Measured in radians per second, it dictates the raw speed of the system, how aggressively it wants to react to an input. The second parameter is zeta, the damping ratio. This dimensionless value acts as the system's brakes, dictating the exact physical shape of the resulting curve. These charts display second-order step responses under different damping states. For zeta between 0 and 1, it's underdamped, overshooting before settling. At exactly 1, it's critically damped, achieving the fastest response without oscillation. Greater than 1 is overdamped, preventing oscillation but reacting sluggishly. These second-order dynamics capture the baseline behavior for the vast majority of real-world engineering projects. The exact same math governs an automobile's suspension rebounding from a pothole and an aircraft's pitch adjusting to a wind gust. By tuning the damping ratio, engineers carefully balance the inherent tension between making a system react quickly and keeping it physically stable. To systematically tune that balance, we map LTI systems onto the S-plane, a two-dimensional grid with a horizontal real axis, sigma, and a vertical imaginary axis, j omega. Poles are roots where the denominator equals 0. Their coordinates are blueprints for natural behavior. The horizontal axis dictates growth or decay. Poles in the left half-plane have negative real values, decaying over time to guarantee stability. The vertical axis represents frequency. Any vertical displacement away from the horizontal baseline corresponds directly to the system's frequency of oscillation. This map plots out specific pole locations for both our first and second order examples. The single red pole sits on the real axis at -2. Padding no vertical displacement, it generates the first-order exponential decay with 0 oscillation. The two blue marks represent a complex conjugate pair of poles. Because they sit off the axis at plus and minus J1.29, they inject that specific frequency, generating the underdamped oscillatory behavior seen earlier. Here we see the system's zeros. Calculated from the roots of the numerator, these coordinates do not alter the natural frequency or the damping, but they shape the transient's initial amplitude and output behavior. When dealing with massive, highly complex equations, engineers rely on the dominant pole concept. Poles situated closest to the vertical imaginary axis decay the slowest, meaning their behavior dominates the entire physical response. If the remaining poles sit far to the left, their transient effects die out almost instantly. This mathematical reality allows engineers to safely approximate complex higher-order networks as manageable second-order systems. By pulling a dominant pole further into the left half-plane, an engineer directly controls both the stability and speed of the final machine. This annotated plot captures an underdamped step response and provides the precise time domain metrics used to evaluate actual system performance. First is the rise time, TR. This defines the duration required for the signal to shoot from a lower baseline to its target threshold for the initial time. The peak time, TP, locates the absolute crest of the oscillation. The height of that crest is the overshoot, MP, which measures the maximum percentage the system travels above the final steady-state target. Finally, the settling time, TS, marks the exact moment the response enters and permanently remains within a tight tolerance band, typically 2% of its final value. Once the transient effects decay, we evaluate the system's final operating condition, the steady-state error. Evaluated as time approaches infinity, steady-state error calculates the permanent numerical difference between the desired target input and the actual output the machine achieved. Rather than solving complex differential equations in the time domain, we use the final value theorem. This Laplace shortcut lets us compute the steady-state error directly from the frequency domain, provided the system is already stable. That error calculation relies entirely on the system type, which is classified by counting the exact number of open-loop poles sitting directly at the origin, where S equals 0. A type 0 system, with no poles at the origin, might track a step command with a fixed percentage of error, but if fed a continuous ramp input, its steady-state error will spiral to infinity. It will fail to track the target completely. Building an automated system requires deciding where to compromise. An engineer manipulates route locations to tighten the transient speed, while simultaneously altering the system type to improve absolute accuracy in the steady state. Ultimately, the balance between a system that is fast but prone to error, or precise but slow to react, is a direct consequence of where its roots reside. Control theory provides the mathematical framework to navigate these trade-offs and drive the system towards its specific design objectives.